Thanks everyone. I have a talk planned, but as usual, I'm happy to go in various other directions, depending on questions and interest. I wanted to tell you about something I've been excited about recently, stemming from some work with Thomas Kreutzig, who is an expert on log VOAs, and my former student, Wenjun Liu, who is now also an expert on log VOAs and many of the TQFT things that will appear here. Let me see if I can get it.
You can make it a little bit.
Why don't I will zoom in on different parts as required. Anyway, so my motivation, as usual, is trying to develop more effective tools to extract algebra and topology and geometry out of quantum field theory. That's right, it's really tiny. In the context I was interested in here, was looking at certain quantum field theories that happen to be topological, which in principle should lead to braided tensor categories of line operators. And then if one is lucky and those categories are sufficiently nice to quantum invariance, along the lines of Azad's talk. Now, the sort of problem with this in practice is that the nicest ways to produce quantum invariance, as in Reshtikin and Turayev's original reformulation of Witten's ideas in Chern-Simons theory, the nicest ways to do this involve expressing your category as modules for a quasi-triangular Hopf algebra, which is the quantum group in quotes in my title. So we had a dinner discussion a few days ago about whether I'm allowed to refer to general quasi-triangular Hopf algebras as quantum groups or not. Unfortunately, physics doesn't give you quantum groups in most of the ways that people have been computing things in physics so far, including in Chern-Simons theory. Some examples of the descriptions that do arise from physics, which are a bit of a mess, if you're trying to extract braided tensor categories and compute, say, quantum invariance. Even in Chern-Simons theory, you don't get a quantum group. You get representations of essentially extended loop group, which than if you introduce a holomorphic boundary condition, as Witten did, when relate to modules for VOA. Then there's a lot of work over the past few decades extracting braided tensor structures on VOA module categories. If you have something that's Chern-Simons-like, but in a different way, Rosansky-Witten theory is defined not by a group, but by geometry, by a smooth, complex symplectic target, Y. And then the category we were talking about is coherent sheaves on Y, that in principle has a braided tensor structure that Roberts and Willerton wrote down. That's very hard to attack explicitly. The things I'll be interested in, that I want, my main example today, will be sort of an equivariant but also affine version of Rosansky-Witten theory, namely 3D n equals 4 gauge theories, labeled by a group acting on a finite dimensional vector space. And then the category we're talking about has many different descriptions. One of them is matrix factorizations on a certain space, which I'll maybe mention later. But it's hard. If you work a little, you can guess a tensor structure on this thing. But getting a braiding is not obvious at all. And so by the end of the talk, I'll try to give a better description of the braided tensor structure on this. I should also say, so 3D n equals 4 gauge theories have two different ways to make them topological. The theories themselves are not, but there are topological twists or topological subsectors that behave topologically, and just as in 2D, there are A and B twists. So my story will be in the B twists, which is algebraic and nicer physically in that there aren't instanton corrections. There's an A side as well, and in principle, everything I say should work on the A side. The category we're talking about on the A side is loop group equivariant D modules on the loop space of V. And that's related to the BFN construction. And I would love to give a version of this talk on the A side, but I don't know how to yet. In the 3D n equals 4 world, if one includes Chern-Simons terms, one starts to attack or get at non-semi-simple actual quantum group rep categories, like the small quantum group at a root of unity. And for some technical reasons, the formalism I'll discuss here doesn't quite apply to that. But I'm hoping a generalization. Okay. So I want to more effectively extract quasi-triangular Hopf algebras. And I'll introduce these things that I call spark algebras to do so. They are formulated if one, I will draw physics pictures. If one tries to turn those physics pictures into precise mathematics, the formalism that includes them is fully extended 3D TQFT. That is my iPad with its new software update flashing. game again.
So there is also connection to information technology or something, right?
Exactly. Lots of money in that right now. At the end of the day, the pictures I draw, interpreted in a perturbative derived context, become causal duality. Causal duality for E2 and E3 algebras, and I'll say a little bit about that. But this is, the formalism has the advantage of being a little more general. It does have a massive restriction in that it requires TQFT that can be extended to a point. And that rules out all Chern-Simons examples. Chern-Simons theories can't be extended to a point. They don't have topological boundary conditions. And this is where I'm hoping that there's a relative formalism that will work. Okay. Sorry, and I also wanted to say, so like the ideas here are sort of closely related to many other, many other versions of Tanakian duality that have appeared in physics over the years. One that sort of inspired me and is closely related is Witten's construction of a fiber functor for geometric satake. There's a whole series of papers now on twisted holography and causal duality by Costello and Paquette, and in particular Costello's work on line operators in various dimensions and integrability is very, very close to all of this in a perturbative context. And use boundary conditions in a very important way. So some inspiration for that actually it came from a thesis of Nena Amans, who worked with Costello, who's a PhD student at Natalie Walls in Copenhagen. The 3D TQFT pictures are also closely related to some work that Theo Johnson-Fried and David Reuter are currently doing on higher linking and braiding. So, right, to start to get slightly more precise. So if you ask the right set of mathematicians how to, given a braided tensor category, how to extract something that looks like a quantum group, they might tell you to find a fiber functor. So there's this thing called the Tanakian principle. It goes like this. If you build a functor from your category to vector spaces, that is a braided tensor functor for the tensor product over C on vector spaces in the trivial braiding. So in particular, it sends the tensor identity to the trivial vector space. Then the category should look like modules for the symmetries, the symmetry algebra of the fiber functor, natural transformations from the fiber functor to itself. And moreover, this symmetry algebra for a braided tensor functor ought to be a quasi-triangular Hopf algebra. So that's the expectation. It's been proven under certain assumptions by various people over the last few decades. So I wanted to take this and incorporate it into physics. where do fiber functors come from? Well, if we just want a functor from line operators to vector spaces, we can get that by vector spaces in QFT come from state spaces. State spaces on some fixed spatial geometry times time. And given a line operator, we can insert the line operator at a point in whatever our spatial geometry is. And that gives a map from the set of line operators to vector spaces with a puncture, well, on spaces with a puncture. And it is functorial. And one can play this game with, say, 3 dimensions, with surfaces with a marked point, or using a boundary condition with a disk with a marked point in the middle. But then you want this to be a braided tensor functor as well, and typically. State spaces on surfaces are interesting and do detect the braiding. That is a great way to. We had an entire talk on mapping class group actions on functored surfaces. Braiding is interesting here. That's not going to give a fiber functor. Braiding is trivial in a disk. That's great. We also want, at the very least, the trivial line, no insertion at all, to give a trivial vector space. And maybe that might happen in a closed geometry, if the geometry is simple enough, like a sphere. Unfortunately, in the case where braiding was trivial, you almost never get a trivial state space with a boundary condition. And the reason behind that is that boundary conditions in QFT are not trivial. They're not like points in a target space. They're Lagrangians in a target space. They never kill everything. They kill roughly half of what you've got. And so to say very roughly what the proposal is, it's to fix the disk picture of a fiber functor by not using one boundary condition, but rather using a pair of boundary conditions that are transverse to each other to fix the red X. So that with a trivial insertion, one gets a trivial state space on a disk with not one boundary but 2 transverse ones. Okay. Now let me be more precise and a little more TQFT. So I'll take T to be a fully extended 3D TQFT. One way to say that is that T is an object in a symmetric monoidal 3 category. And we've also, as another object, the identity in that 3 category, you've got the trivial 3D TQFT. When I say boundary condition, what I mean is one morphism in this 3 category between T and empty, or empty and T. And I want 2 of them that I'll call N and D. Whether they go from empty to T or T to empty doesn't quite matter, as long as there are sufficient orientability or dualizability conditions imposed. So there's some duals that go the other way. And I need them to satisfy some properties. First, there's this sort of transversality that I mentioned, and in this sort of picture, transversality means that the composition going from the empty theory to T and back to the empty theory is trivial. It's an empty or trivial two-dimensional TQFT, or it's the identity interface between empty and empty. Another way to say that, an equivalent way to say that. So N and D orientation reversed are objects of the same two category. There's a two category of morphisms between T and empty, and one can take Hom in that two category, you get a one category, and that one category had better be vect. That's the transversality. I'll use a local version of that, but I think at the level of this talk, it's not super important. What I mean by a local version of that, which is implied by what symbol means above. By local version of that, I mean I not just collapsing entire boundaries, but collapsing or touching little bits of boundaries together. Like pushing my fingers through a sandwich of theories cancels them, and I can poke holes. Local transversality. And then you might ask, great, well, what happens if you stack the boundaries the other way and go from T to empty and back to T? Well, that's almost never going to be the identity. It'll be something really big. But what you could require instead is that there's a deformation of this stacking that's equivalent to the identity, and then you have to say deformation in the right way. In general TQFT formalism, there's a notion called condensation, which can be expressed as the existence of a particular morphism, of a one morphism between the stacking and the identity. But it's really a one-way operation. In a DG context, this is a deformation by a certain Moore-Cartan that deforms an algebra of operators here to whatever lives on the identity. This other thing I'm requiring that you can sort of glue going the other way is going to be necessary for functors to actually be equivalent. So I'm calling it completeness condition. So just in case it helps, two examples to have in mind of this sort of setup. If T is some topological gauge theory that sums over G bundles, then N and D can be taken to be Neumann and Dirichlet boundary conditions for that gauge theory that either say continue summing over G bundles at the boundary, if it's Neumann, or fix a trivialization of the G bundle at the boundary, that's Dirichlet. And these are transverse and can be glued back together. Another example, which also shows you how restrictive this is the sigma model world in Rosansky-Witten theory. Boundary conditions are labeled by holomorphic Lagrangians. Transverse literally means transverse, and that's fairly easy to find. But well, if X is you can ask sensibly the geometric question for what sort of X admits transverse Lagrangians. If X is suitably non-compact, that'll happen. But the completeness condition in particular implies that both of the transverse Lagrangians generate the entire two-category that Kapustin-Rozansky and Salina wrote down for Rozansky-Witten theory, and that's actually highly restrictive, and more or less requires X to be affine. There are generalizations of this, I think, that will work just fine, taking X to be a cotangent bundle to something projective. It just not technically in the form as I'm describing.
Second question, should one think of the category of boundary conditions as some kind of 2D TQFT with defects? How should one think conceptually of the category of boundary conditions?
Yeah.
Is it something like a 2D TQFT plus defects?
Yes, exactly. It's That's the two category. So it's not one 2D TQFT, but there are many. It's like this quilted picture. So you have many different 2D TQFTs. There are multiple boundary conditions, and between any two of them, there's a category of interfaces. Yeah. Thanks.
Sir, so when you say about transversal, so they really need to intersect in one point?
Yes. Yeah, so yes, but they're easy generalizations where they might intersect in a few different points transversely, and then you sort of work over matrices. So like purely transverse in one point is actually going to be enough for the gauge theory examples that I wanted to apply this to. But yeah.
Maybe in interesting cases you can't find, like, maybe you can find two Lagrangians which are transverse, but like intersect at many points.
Yeah,
That's kind of
I think
general.
that's an obvious generalization. Yeah, so to I guess no, to expand on Nishi's question. Given this data, if this is what you know, there are three categories around. There are three one categories, standard categories. There are line operators on each of the boundary conditions and line operators in the bulk. And the way to say that in this extended formalism is endomorphisms of this object in a two category called Dirichlet, endomorphisms of this object in a two category called Neumann, and endomorphisms of the identity interface in the bulk. It's also an object in the two category of self-interfaces between T and T. Other ways to say it as well. And my claim is that it is actually nice to play with all of these at once. They're all monoidal. There's a tensor product. The tensor product is in the description above is composition of palms. They're endomorphisms. Compose. In pictures, it's collision of parallel lines. Moreover, the one in the middle is braided. It's monoidal it's actually monoidal in an S1 of different ways. And the picture for why it's braided is literally braid. Lines around each other that defines a morphism. Okay. And given the completeness condition, I put on boundary conditions, which is really strong, and it makes them generate. One one then expects the Drinfeld centers in a suitable derived context, as in Kostia's talk, the Drinfeld centers of both of the boundary categories to be equivalent to the bulk category. So this is all standard, at least in a certain subset of the literature. It's formalism for expressing a certain set of ideas. What is still difficult is that the descriptions of these categories may not involve Hopf algebras.
So this n should be in some sense dual to G? Or you don't know?
Say again?
So n and Z should be dual to each other in some hierarchy purpose.
Yes.
And this map.
But that duality is the transversality condition.
That's right. For example, you need some kind of, so you have the structural map and you stack them like this or like that, but you need some kind of zigzag relation.
It's at the top level, it's nothing more than what I said. But that ends up implying lots of interesting dualities at lower category levels.
But it's correct that like n is really dual to G in my purpose.
Yes. So in particular, you see a version of, well, I think the thing I will tell you is actually a version of this duality at the level of categories. So just again to orient a bit. So if we're talking about topological gauge theory, the simplest example is for a finite group. Then there are no complications. It's called Digraph-Witten theory. Then lines on the category of lines on Dirichlet looks like sheaves on G or G-graded vector spaces. The simple objects here, labeled by elements of the group, just tell you how to change the trivialization. So D trivializes a G bundle, and as you move across a codimension 1 manifold, you can change the trivialization by an element of the group. And that's what the objects in here are. On N, the category is rep G, or sheaves on point mod G, and these are Wilson lines. They measure the holonomy of the bundle along the support of the line. And in the middle, one gets the Drinfeld center of either of them, which is sheaves on G mod G. And so these two categories, sheaves on G and sheaves on point mod G, are dual in a certain sense as well. Okay. So I'd like to incorporate fiber functors into the pictures. So to do that, I evaluate a state space. Suppose I want a fiber functor for lines on N. I can take any line on N and evaluate the state space on a half disk surrounded by D on the other side. This transversality, so here's another way to say that. Just taking a spatial slice. So I'm taking a line and evaluating the state space on a half disk with a marked point labeled by the line on the N boundary. This is monoidal. and ends up being a good fiber functor precisely due to transversality. So there is that poke my fingers through to create a hole trick, which I can now extend to sort of karate chop the cylinder in half trick using transversality between D and N. The middle bits cancel, and so the functor applied to a tensor product of two lines just becomes the functor applied to two lines individually, which is a tensor product over a tensor product in vector spaces. That's where transversality becomes important. And so in a similar way, one gets from transverse boundary conditions by functors for lines on the other side and on lines in the bulk. By evaluating again, a state space on an actual disk with a line in the middle, or a different half disk with a line on the D side. Okay. And then the natural question to ask is what are the endomorphism algebras of these fiber functors if we want to apply Tanaki formalism? And right. So the expectation, given this functor that's like sort of caps a line with D, endomorphism of this ought to be given by lots of physics words come to mind. I need to say operators somewhere. They're given by operators supported away from the line. So anything in a complement, anything in this picture that's sitting in a complement of the red line. And everything is happening in sort of a moment of time. So they're going to be operators supported in a complement of the line in a moment of time. So they're sort of supported in a little arc. A different way to draw that is like this. To the extent that excitations or operators on the boundary make sense, any operator that can be inserted along the D boundary that stays away from the line, it can touch the end bits of N, will act as an endomorphism of this functor. So there's a sketchy physics definition of what this endomorphism algebra ought to be, which I'm calling a spark algebra on D. As a vector space, it contains all excitations that look like this. They're supported on a little arc, and their product is given by vertical collision. This produces an associative algebra. I think of these as like electric sparks or arcs sort of moving along to nearby wires, sort of going up and down. And I initially thought, these should obviously be called arc algebras. And then I realized I'm not allowed to call them arc algebras. So they're spark algebras. All right, here are two equivalent and maybe more precise ways to say what this is. Flattening out a neighborhood of the D boundary. One can ask, like, where do these things I'm calling operators on an arc or on a little interval come from? Well, they ultimately come from lines on D that are turned sideways and end on bits of N. And so one can in principle obtain HD as a decategorification. In this case, it's an interval version of factorization homology of CD. And this is where the connection to causal duality comes in. If you formulate this under some extra assumptions, you end up with a bar complex. And if you know what local operators are and formulate this correctly, you end up with a bar complex of local operators on the other boundary. The other way to say this is by what's called a state operator correspondence. So as a vector space, if you don't want to think about what an operator on an arc is, you can instead think about states on a rectangle. The rectangle is the link of the arc. So if we take a neighborhood of the arc, it looks like a little tube, and a boundary of the neighborhood of the arc is a rectangle with two very long ends on D and two very short ends on N. And that's what that is.
Why is tau in that? Why is tau on the inside of the rectangle? Does the rectangle lie on the boundary, or does it somehow?
So the inside of the rectangle is sitting entirely in the 3D theory. So L is not there at all. This is equivalent for any L. So
Maybe could you maybe just draw where the rectangle sits in that picture?
Yeah. So I guess I have a thing. I can just draw it here. So the rectangle is here.
Okay, great.
Yeah,
I think I understand now.
And so similarly, so that, sorry, we need to kind of show the whole thing. So that was sparks on D. That was endomorphisms of the fiber functor for N. Similarly, there's sparks on N, which are states on a rectangle that looks actually the same, that are endomorphisms of the fiber functor for D. And then you can ask, great, well, what are endomorphisms of the fiber functor in the middle? And that states on an annulus that's glued out of the other two rectangles. And these, because the rectangles are the same, as vector spaces, these are, there's a change of orientation. They're just dual vector spaces. The thing in the middle is the tensor product of those two vector spaces. Okay, so what other structure arises from this? So this is a fun by picture part. I'll make some claims. I think I'm going to skip through many of the pictures. So first, these spaces of states on a rectangle are Hopf algebras. I got excited about this and then looked it up and noticed that David Reuter actually gave a talk on precisely this at Perimeter in 2017. Though I think some of that it never made it into a paper. Some of it will be in his work with Theo Johnson-Fried. But there's a formal proof in 3D TQFT that the space of states on a rectangle with transverse boundary conditions is a Hopf algebra. Moreover, they're not just Hopf algebras, but if you consider both of them at once, they're Hopf algebras with a non-degenerate Hopf pairing. And the Hopf pairing in pictures is given by evaluation on a 3-ball with N on the northern hemisphere, D on the southern hemisphere, and the two different sparks on one hemisphere or the other, sort of linked with each other. And this ends up satisfying all axioms of Hopf pairing. Call that Hopf pairing H. And moreover, without knowing anything about categories or where these came from, purely within 3D TQFT, defining the spark algebras this way, the spark algebra in the middle, which as a vector space is the tensor product, is actually quasi-triangular. It's the double of the spark algebra on either side, and it has an R matrix, which independently from pictures ends up being given by the inverse of the Hopf pairing. And so part of the game here is topologizing some very old ideas.
How do you know that the pairing is non-degenerate?
Because as vector spaces, they're dual because the rectangles are the same up to a change of orientation. Getting the R matrix as the inverse of the Hopf pairing uses completeness conditions on boundary conditions and gluing. Okay, and then finally, the categories are what they're supposed to be. So the easy part is showing that there are functors from each of the line categories to modules for the respective spark algebras. The non-trivial part that requires completeness of the pair of boundary conditions is showing that these functors are equivalences. And then I had made remarks about causal duality in the perturbative setting. I think the coolest thing to come from that is, maybe for my understanding, I've heard for years that it's expected that that the associative causal dual of an E3 algebra is supposed to be quasi-triangular Hopf, where the R matrix has something to do with the E3 bracket. And in this formalism, that just becomes blatantly obvious. Working in a perturbative DG setting, the Hopf pairing is actually given by a certain shifted Poisson bracket, and then the R matrix is the inverse of that.
You say it's double. In what sense is it? Dirichlet double?
Yes,
Oh.
Dirichlet double. And I'm being very ambiguous about derived or not derived things, because the pictures and the formalism works for both. Okay, I'm going to show you some pictures, and then I'll finish up with examples. So like, why does any of this work? So why is the spark algebra Hopf on one of the two sides? So the product comes from vertical collision. The coproduct comes from inclusion of a spark in a double pair of pants, and there's an antipode as well. And then you've got to check stuff. you want to check that the coproduct is co-associative, which is easy. And then you need to check that the coproduct is an algebra morphism, which requires poking a hole through this double pair of pants cobordism using transversality. We mentioned category equivalences already. I think I'm going to skip over that. You say, yeah, I'll say a little bit about the hop pairing. The case where I can actually say something sensible about non-degeneracy is on the finite dimensional, if they happen to be finite dimensional. And if they're infinite, when choices have to be made, and the representation categories are also very subtle in that case. Anyway, there are pictures. I think I actually want to finish on time, but I'll show you my favorite picture. So there's this formula that one finds in books about Drinfeld doubles. So you form a Drinfeld double by like answering together a Hopf algebra and its dual, but you need to know how to commute an element from the Hopf algebra with an element of its dual, and that commutation relation is really horrible. It tells you that if you, here are the things that are involved is the D-spark algebra and the N-spark algebra, and if you swap the two, you get some horrendous formula that involves a triple coproduct and the Hopf pairing and the antipode. And it works algebraically for sure, but it's got a pretty picture. So that boils down to the double in the middle is sparks on two sides of a cylinder, and if you want to move them past each other, you can do that up to a correction at the ends, and the correction at the ends, because of transversality, can be factored off into two little three balls, and the two little three balls are Hopf pairings. And because of a change of orientation, one of them has an antipode stuck in. And so there's a fun interpretation of that old formula. And then the R matrix being the inverse of the Hopf pairing comes from expressing the R matrix geometrically. It's defined by this pair of pants that's twisted up a bit. And that can be obtained by gluing two cylinders across a box, and it turns out that the box gluing involves the inverse of the Hopf pairing. So that's what I mean when saying it. Like everything sort of falls out from topology in a nice way. Okay. So fun setup. What do we do with it? We can recreate some known things. In finite group gauge theory, so recall that N and D stand for Neumann and Dirichlet. Either don't do anything or trivialize boundary bundles. Suppose I didn't actually know anything about categories of line operators and tried to just find the sparks. As a vector space, the sparks come from states on a rectangle, and that's a computation. So this ends up being the vector space generated by the finite set of G bundles on a rectangle that's trivialized at the two Dirichlet ends, and that's just elements of the group. So as a vector space, that's the elements of the group. Um, and then as algebras, one goes in and asks, like, what are the actual sparks? They're, on Dirichlet, they're changes of trivialization. And their product is the group product, and one ends up with a group algebra. On Neumann, the sparks are they're parallel transports on an interval trivialized at the two ends, and one ends up sort of summing over all choices of trivialization. Each choice of trivialization at the two ends gives you a different spark, and that's just a sum over irreducible representations of G. And that's another way to get something that as a vector space looks like the elements of G. But now the algebra is functions on G. And so one can compute coproducts and everything very explicitly, and an R matrix, and then recover the classic story involving Drinfeld doubles of either functions on G or the group algebra, and the respective representation categories. So something that is nice, if your perspective is my perspective, which is being handed a TQFT where you can't compute everything and you need to extract something mathematical. And a nice point here is that it sort of really structures the information you need to actually compute, like the minimal amount of stuff that you need to make things go. Like computing everything is way too much. It's enough to know one of the spark algebras as a Hopf algebra, or both of them as algebras without the coproduct, or know something about one of the categories, or whatever. And I'll finish with the B-twisted gauge theory example. So this is a lot like finite group gauge theory. And for finite group, all bundles are automatically flat. Here, G is a Lie group. I'm going to switch notation and write G to be the complex algebraic group. And then this is still a theory, roughly, of flat G bundles and constant sections of an associated V plus V dual bundle. It's cohomologically non-trivial. There's a homological Z grading, and there's a separate Z2 grading that controls Koszul sign rules, parity. N and D are the same as before for gauge bundles. Either don't do anything or trivialize a G bundle and set the connection to 0. And then restrict the sections to either lie in V or V dual. Those are two transverse choices that one can make in gauge theory. And then there are computations, and the computations actually involve a bit of genuine physics. I'm giving an answer that is naive, and it's correct because there are no Feynman diagrams that contribute to this answer, and one can actually prove this is, there are no corrections to this. Let me just summarize. So the spark algebra on D roughly looks like the group algebra of G, but the modules for it This is where things are infinite dimensional, and you have to be careful about the categories. If one actually looks at the line operators that this is representing, those line operators are finite dimensional reps. And so they're reps that are algebraic, rather than all reps for the group algebra. And another way to say that is reps of the enveloping algebra that are integrable. Semi-direct product with an exterior algebra in the vector space, which ends up landing in homological degree 0. Weird because homological degree is unrelated to the causal sign rules. The spark algebra on N is functions on G times an exterior algebra in V dual. And there's a slightly non-trivial code product here that mixes the two. And then the two combine into a quasi-triangular Hopf algebra in the middle that enveloping algebra, remembering that we want integrable reps, and then functions on G, and an exterior algebra on V plus V dual, with some extra relations. And an R matrix that looks just stupidly simple for me. And the most surprising part of this is that this really simple R matrix that one might have guessed up to reordering some factors is actually correct. There are no corrections to it. And that ends up being, so the derived category of modules for this thing is a partial causal dual to the matrix factorization category that I wrote before, and once one passes through that causal duality, this R matrix just gives you the braiding, which I find really nice. There's a miracle here, so I'll end. There's a miracle that the Hopf algebras involved in the B-twist of any 3D n equals 4 gauge theory, abelian or non-abelian G, any representation. The Hopf algebras are all in homological degree 0. And so it looks like there's an abelian truncation that makes sense of the Hopf algebra rep categories. Of course, that doesn't survive derived equivalences. And so if you want to work with matrix factorizations, you need to work with the fully derived thing. In general, I would not expect the Hopf algebras obtained this way to be in degree 0. There's just something super nice. A special case is Azat's example. If you take the group to be trivial and B to be C to the n, you get his simplest non-semi-simple Hopf superalgebra. If you take the group to be GL1 and B to be C, this reproduces quantum GL11, but derived. And sort of what ought to be a really fun example, if you take the group to be GLN and B to be the Lie algebra times the fundamental, the category in the bulk has a quotient to, or a stable part that is sheaves on the Hilbert scheme. And that quotient is a quotient by a tensor ideal. Unstable things form tensor ideals, and it would be really cool to actually spell that out. Not something I know how to do at the moment, but that's very important to many people. That category and its use in categorification is important to many people here. Sorry for going over. Thanks.
Quick questions for tutor? Yeah.
You get these 3D toroidal algebras which arise from torical ideal three-folds. I mean, GL1 hat is an example, GLM-N hat is an example.
It's a different direction. So really closely related to that, I think, because logarithmic VOAs are involved, at least the ones related to toric Calabi-Yau 3s, and divisors. And so one thing we're also trying to do is to like bootstrap this onto free field realizations. There are complicated ways to get Kazhdan-Lusztig correspondences for VOA modules. Like how do you go from VOA modules to modules for a quasi-triangular Hopf algebra? That is another question one can ask. Ideas like this, I think, will be useful in answering that in a slightly different way than has been done so far. This is not the same. This is not affine. This is related to affine GL11, but that's sort of a coincidence here.
So related to this question, do you have a description of everything you can obtain as a Spark algebra? Like, for example, can you obtain UQ of G, or is it a generalization of everything we know? Or?
No, it's not. So far, it's just strictly what I've mentioned today. Will only give you things that look like Drinfeld doubles.
Okay.
UQ of G is at best a relative Drinfeld. Exactly. And I think that's totally fine. And there's the generalization where you don't use a fiber functor to vect. You use a fiber functor to models over the Cartan. And
you get all Drinfeld doubles.
And I think so. That's kind of sort of new, and that's the thing we're working on.
Do you know exactly what you have to modify to get this bounded derived category of coherent sheaves and this Hilbert scheme of endpoints on the complex plane will localize to like a y equal to 0, x equal to 0 along a line or along a curve? Do you know exactly what to modify to get that? Where you get Hilbert scheme on the complex plane, but you're restricted to one of the, like along a line, along the line on the complex plane.
Sorry, I think the answer is yes. I mean, that's a subcategory, I think. But I haven't thought about it that much. But I think the answer is yes.
Okay.
I think we should save the rest of the questions for the coffee break, unless your question is short. Okay, yeah, cool. 20 minutes and...